The following are responses from an experiment with treatment groups. In this experiment, it looks like there are 3 treatments, A, B, and C, and there are 4 units in each group. So that means that I is equal to 3 and J is equal to 4, where we have 3 treatments and 4 observations within each treatment. We want to know if there is evidence any of the treatment means differ from one another. So that means that our null hypothesis is that each mean is equal to each other. So mu A is equal to mu B is equal to mu C, and the alternative hypothesis is that at least 2 means are different from one another. And so we can use software to obtain an ANOVA table that includes our F test statistic and p-value to decide whether or not we should reject the null based upon a significance level of 0.10. So let's go ahead and move on over to our R program so that we can do this in software. The first thing we need to do is enter in our data. So the way that we do this is we put in our response as a complete vector first. So the vector of just the responses from the treatments is combined with the command using C. And so the first 4 observations are going to be for treatment A, and the second 4 for treatment B, and the third 4, or the last 4, for treatment C. So we have 3.5, 3.4, 3.8, 3.5, and so on. And then we need to define the response values, and then we need to define the treatment. So we can do this by just repeating A 4 times, repeating B 4 times, and repeating C. This would be the same as just writing out A 4 times and B 4 times and so on, but it's a little shorthand to just use the command rep, means repeat this thing 4 times, or however many times you verify it to, or tell it to repeat. So we want to combine then those again with the command C so that we have a vector of treatment values or treatment names, and then we can combine our data using the cbind command. So we have an entire vector. We want to make sure that treatment is included as a factor. So my.data is what I'm going to call it. If we want to look at that, we can see all of our response values and then the different factors 1, 2, and 3. All right, so let's go ahead and create a box plot to look at these different treatment groups. We can see that A, B, and C are all together. It looks like the variability might be slightly different between the groups, but it's such a small sample sizes that it's kind of hard to tell. And so we're not going to really make any assumptions about that other than we're hoping that they're about the same. The means definitely look different for each group, and it looks roughly symmetric for each group. This one is a little bit skewed, but we're going to assume that our conditions are met in order to do a single factor ANOVA F test. Let's go ahead and first look at the means, the variances, and lengths though for each group. We can do that using the aggregate command. It separates out each command, and we can see that the mean response for treatment A is 3.55, for treatment B it's 3.825, and treatment C it's 3.47. So B seems to have the highest treatment response and C seems to have the lowest, and so we're going to expect them to have the largest difference between them. Our variances are also 0.03, 0.009, and 0.015 approximately. So if we look at these, they should be about the same. They're a little bit different, but again, we have such small sample sizes, only 4 for each group, that these might vary a lot more than they would if we had larger sample sizes. So we're going to assume the equal variance condition is met. And then lastly, we need to get our ANOVA table. And so the AOV command will do the most of it for us, but if we look at this, it doesn't quite give us an ANOVA table. It just gives us our sums of squares and the degrees of freedom for those. And so that isn't quite what we want. We'd like it to be a little bit nicer. So by calling this something, and I've called it just mod for model, and then running the summary command for the model, we'll get a nice table of values. So we'll get the ANOVA table. The only thing that's missing is the total row, but it gives us the mean squared, the mean squares, the sum of squares, except for sum of squares total, which we could get just by adding these two together, and more importantly, the F test statistic and the p-value for the test. So looking at this p-value, let's go ahead and copy this over to our analysis over here. And we can see that our p-value is quite small. It's quite small. So what that means is that we are going to reject the null hypothesis, because it is smaller than our significance level. We have an F test statistic of 7.409 from a F distribution with I-1, so 2 and 9 degrees of freedom. And so what this means is that there is moderately suggestive evidence at least 2 of the means at least 2 of the treatment means differ. So if we wanted to take this a step further, we could do a multiple comparisons procedure and see exactly which means differ and by how much. Here, we're just doing the overall F test and seeing if one of the means is different from the others. And sure enough, we get a significant result with a p-value of 0.0125.